thank Dr. Sujata, Mr. Bharat, and the entire team of Young Innovators as well as MP Birla Institute for Fundamental Research for putting together this program and also for giving me an opportunity to be here with you. So my name is Madhusudan. I work at Jawaharlal Nehru Planetarium, and I would like to be identified as a teacher. I am not an astronomer, not a researcher. I am a teacher. So I read, I understand, and I communicate that to children like you at various age groups, from third standard to post graduation. So we have many programs at the planetarium, and these programs are all aimed at preparing students for a career in science education and science research. It's not only astronomy. Astronomy comes incidentally, but the focus is on fundamental sciences like physics, chemistry, mathematics, biology, and so on. So if you have a good fundamental understanding of these subjects, you'll automatically become a good astronomer. Okay, so you have to be good at these physics, chemistry, mathematics, biology, the core subjects, and there are many others, of course. You can't leave out, study of rocks and minerals, what's it called? Geology. Yeah, so you can't leave that out. So all in all, you make use of all the knowledge that you have gained out of all the other branches of science, and you export that to astronomy. But astronomy is not a passive receiver of ideas from other branches of science. Astronomy has enriched other branches of science through some very interesting phenomena that we get to see only in the realm of astronomy. As a result, the other sciences have also become enriched. So this bonding between astronomy on one side and other sciences on the other side is very, very strong, and the benefits are always going back and forth. Okay, so you need to be good at both finally. So we have many programs towards this end in the planetarium to help students to take up a career in science, and I teach in some of these programs, most of them. So that's how I identify myself more as a teacher rather than a researcher who I am not. Okay, so that's my introduction. So now for today's program, I know that you are having a 2-day workshop on assembling a telescope. So assembling a telescope is more or less like a Lego blocks. You have various blocks and you know how to put them together and get something to work. You have a certain fixed objective, and the blocks are put together to make it work. So in the same way, you are also going to assemble a telescope here, and as Mr. Bharat was telling right at the just before the commencement of this program and the conclusion of the previous one, the way the telescopes used to be made were more arduous. It was a week long or maybe almost 10 days work to put up to make a telescope from the scratch, so to say. But now it has become very easy. So it's not enough if you have a telescope, you also need to know what you do with the telescope. I'm sure there will be a number of sessions between now and tomorrow where you'll be told as to how the telescope that you make can be put to use in a number of different ways. So there will be a few things which I will touch upon, not entirely, but mostly I'll be discussing with you what are the principles on which, optical principles on which telescopes work. Okay, and to keep matters simple, we'll be discussing mostly in the context of optical telescopes. I'll quickly tell you what we mean by optical telescopes, and the same principle more or less can be extended to telescopes of different kinds. Okay, the basic fundamental operations of a telescope depends on the same set of principles, whether it is a space-based telescope, an optical telescope, which is a ground-based one, or there are other kinds of telescopes like infrared, radio telescopes, and so on, UV telescopes. So the principle of operation are more or less the same. So where do we begin our story? We begin our story in the 17th century, at the beginning of the 17th century. when two very important inventions happened. So one is Galileo's telescope, which came in 1609, and I don't remember the exact year in which Robert Hooke came up with the microscope. Now these two instruments revolutionized the way we looked at nature in two extremely different ways. When we say extremely, in this case it is literally extremely, because on the one hand you have the telescope, which made us to look at objects that were very far away from us, but which were very faint, so faint that our naked eye or unaided eye could not observe them. So it enabled us to see such objects, observe such objects. And on the other hand, you have the microscope, wherein the objects are very close, they are within our physical reach, but yet they are so small that they are still beyond our vision, our sight. So the evolution of technology made microscopes to get better and better, which contributed richly to the growth and development of biology, especially biology of microbial nature, of very small size, and the evolution of technology which led to growth and development of telescopes made us to shrink distances, as to say in astronomy. So you could see farther objects much closer, fainter objects much brighter, and smaller objects much bigger. So in these two radically different ways, the two inventions of the 17th century completely changed the way we do science. And how our interest will be only on telescopes today, and the way the telescopes have actually revolutionized our understanding is something that is of great interest to many people. But today we will not go into so much of those details. We will stick to those optical principles on which these telescopes work. Okay, so there you have a typical telescope. This is a standard picture stolen from internet. So the story of the evolution of telescopes is more or less a story of the growth and development of optics. Now this is a very strong statement. It is not merely something being told about telescopes. If you look at how telescopes came into existence and how the telescopes were made better and better, because telescopes in the form that we had earlier had certain problems, and these problems could not have been solved without a deep understanding of optics. By the way, you all know what optics deals with? What does optics deal with? Light? Lenses? Okay, for the time being we will accept this answer. We will slightly modify later. So light, it depends, it deals with light. Okay, so you know so much about light and properties of light, like reflection, refraction, interference, and there are a few others which you have not yet probably come across, but I will introduce to you in a very simple manner, which are called interference and diffraction, and also something else called polarization, which I will not discuss in today's session, but this is something for you to know. So these are all properties of light. Each and every one of these have been enriched. We have been able to understand mainly because of our curiosity to understand how to make better telescopes. Okay, so it has contributed a lot. And then as we understood more and more about light, more and more about other things, what light does with matter and how light interacts with matter, we learned to make better telescopes. Okay, so it's two-way. So physics got enriched because there was a problem on hand that we wanted to make better telescopes, and telescopes became better and better because our physics of optics or physics of light got better and better. So this is a way in which most of the time science goes. It doesn't go in isolation, one subject alone going up. That will depend upon inputs from many other branches of knowledge in science. So what is a telescope? Can somebody quickly tell me what a telescope is? Yes?
Telescope is a device which with the help of mirrors and lenses helps us to see objects which are far away from us in a magnified way.
In a magnified way. Okay, underline that, magnified way. Now, you have anything else to add to what he said? So more or less the same. Okay, so one thing is that you see distant objects, and the other thing is that he mentioned about in a magnified way. So we will look up these things as we go along. Okay. So a telescope helps us to see astronomical events back in time. That's another important thing, because when you look at an object which is very far away from you, you are basically receiving light emitted by that object, and that light has to reach you. No matter how close the two objects are, the observer and the source of light, there will always be some finite time that light takes to travel between 2 points. Okay, this is the essence of Einstein's theory of relativity. Okay, lot of things that I mentioned today maybe you have not studied in the school, but just if you remember, and whenever it is done, you will recall, okay, this is what was discussed in this workshop. Okay, so Einstein's theory of relativity says that even light has a finite speed, and to travel howsoever small distance, even between you and me, light does not go instantaneously. It takes some time. So if you are looking at me now, you are not looking at me as I am right now. You are looking at me as I was. You have to calculate. If you know the distance between you and me, and you know the speed of light. What's the speed of light, by the way? 3. Okay, depending on whether you have read Indian book or an American book, you'll have different ways of expressing. 3 into 10 to the power of 8 meter per second, or 300,000, is it kilometer? Kilometer per second. So 300,000 kilometer per second. What's the distance between you and perhaps the last row boy sitting there? What do you think is the distance between us? 10 meters. Sir, ಎಷ್ಟುದ್ದ ಇದೆ ಇದು? The dimension of this. Okay, let us take 10 meters. Okay, let's take 10 meters. It's not 10 meters. For simplicity, we'll take 10 meters. So what will be the time taken by light which falls on me to be received by an observer there? So all you have to do is distance traveled by time taken is speed. So time taken will be distance by speed. Okay, so 10 meters divided by 300,000 kilometer. It will be a very, very small time, but it is not zero. That's what you should appreciate. It's not zero, it's greater than zero. So some time it takes. Therefore, you'll be seeing so many seconds or so many nanoseconds or even picoseconds, whatever it is, back as I was. So you'll never see me as I am right now. Now when it comes to astronomical objects, this time difference becomes enormous, because there are objects which are so far away that light takes a few years, a few months, a few days, a few weeks, and sometimes a few millennia, thousands of years. So if you are looking at that object which is taking thousands of years for light to travel from there to Earth, it means that what you are seeing now is as it was so many thousands of years back. So a telescope transports you back in time. Okay, these are all standard phrases. These are not my phrases. Okay, you will find this elsewhere also in books and other places. A telescope also is said to bridge space and time. So somebody said that it makes things appear nearer to us. So it's as though the space has shrunk between the object and you, the telescope and the object, and also it takes you back in time. Okay, these are all very, very nice things to know about what a telescope does. It's not just a dummy tube, a PVC tube with a mirror at one end and eyepiece at the other end, and somebody else peering through the eyepiece. It is a lot more than these things. It also enables you to see new objects and new phenomena. Okay, so some of the phenomena which you might not even know that it can exist can be seen with the help of telescopes. So a telescope is a device that does a lot of things. And if you fit a telescope with a prism or a grating, I'm sure all of you would have seen what a prism looks like. Okay, this is a glass prism. I'll circulate this to you at some other appropriate time. So this is a glass prism, and then this is a grating. Okay, the two pieces of glass. Between the two pieces of glass, I have put a plastic sheet which is called a grating. Now what this grating and a prism does is to help you understand a number of things about astronomical objects. In fact, almost everything. Almost everything. If you want to know what, suppose you are looking at a star. With your naked eye, you just look at a star, some light coming from the star, reaching your eye. So you just know there is a point of light. But you make that light pass through this prism or a grating, and if you understand the language of light as it passes through this, the changes that happen in light when light passes through a grating or a prism, with that you can get a library of information about the source. You can find out what chemicals are there, which chemical is more in abundance, and then how far away is it? Is it moving towards the earth, towards the solar system, or away from the solar system? And at what speed is it traveling? And how far away is it? What is its brightness? Lot of information. And with this information, you can build a lot of theory which will tell you how a star comes into existence and how a star eventually stops producing energy. And in between the birth of a star and final stage when it is not able to produce energy, what are the various changes that happen? Everything can be monitored, everything can be understood. If you just put this piece of plastic or this piece of glass into your telescope. Just putting is not enough, you should understand the language. It's like handing you over a book, you don't understand the language. If I ask you, can you please explain the contents of the book? Would you be able to tell me the contents of the book? No. First you have to understand the language in which the book has been written, and then you have to understand the meanings of the words. These are all things that you study as a good student of science in your high school, in your +2 and undergraduate program. And by the time you have enough knowledge of optics about what light undergoes through while passing through a grating or passing through a prism, you will have understood how astronomical objects actually behave. Okay? And for all that, a telescope is absolutely essential. If you just look at a star through a grating, you may not be able to understand all the details that I told you. So a telescope would be absolutely essential. Okay? And all the things that I mentioned so far about the telescopes will help you to build a model of the universe as we understand it. So if somebody asks you what is universe and how did universe come into existence and what will happen to the universe in its final stages, if there is a final stage, all these things you'll be able to understand directly or indirectly with the help of what you observe through a telescope. So a telescope is not merely something that you build and then you look through, take some pictures, post it on Instagram and then get 1,000 likes. It is a lot more than that. It is very, very enriching, and you will find it yourself with passage of time once you have the telescopes tomorrow, and then you put the telescopes to proper use. Okay? So someone told me that even faint objects can be seen. So on the left hand side you see this is a constellation of Scorpius as unaided eye would see, without any gadget attached to your eye. And if you were to see through a telescope, not this rich, this is actually a photograph. Mr. Ravi will immediately tell, Bharat is there, they're all experts in this field. They'll say, no, this is a long exposure photograph, this is not how you see through a telescope. That's another thing, with the help of a telescope and a camera, you can get a lot more details which you might not see at the first instance through a telescope. Okay? Once you see through the telescope, perhaps it will not be much better than this. But you put a camera to that, and then if you know how to photograph, somebody is going to, I think, talk about that also?
No, sir, not yet.
No, not yet. Not there. Okay, that is for another day. Then you will see such rich details. So you see so many objects which are here are not visible here. So this is what we meant. So new objects can be identified through a telescope. Now suppose you are in the 17th century or 16th century, let's go one century earlier, 16th century. Nobody knows anything about what a telescope is. Do you think it is possible for anyone to even imagine that a device like this can be built with the help of lenses and mirrors which will help us to see astronomical objects? Can you even imagine that you put together these things and do it? What's your opinion? Can you imagine a gadget which is non-existent now? Okay, let's not worry about telescope and 16th century. Even right now, can you think of any gadget which doesn't exist, but in your imagination you come up with a gadget? Yeah? Huh? Again, that knowledge is already there. Knowledge is there. You know that teleportation is something that you want, but then you don't know how to do it. Okay, now on a small scale people have achieved even that. Okay, quantum scales. But to make a device like this and then see that this is how it should function, it's very hard to imagine. Okay, so not surprisingly, the first step towards making a telescope was a serendipitous one. Do you understand the meaning of serendipity? Anybody? Serendipity means a chance discovery. So you are not actually trying to discover something. You are doing something and you are so lucky that you notice it. Huh? Accidentally, it's an accidental discovery. But accidental discoveries are not all that accidental. If you don't have a prepared mind, suppose you are not thinking about it, even if something comes right in front of you, you will not even recognize that it is something new. To recognize that this is something new, to recognize that this is very powerful, to recognize that this is something out of the world, you need some intelligence. So only luck is not going to help you. Okay? So even here, the story goes that the telescope was actually accidentally discovered by Hans Lippershey when he made a spyglass. Okay, I think I have a picture. Yeah, this is a spyglass. As the name itself says, it can be used for spying. So you are not seen by the distant person, but the distant person is visible to you. So that's a spyglass. So this was accidentally discovered. But then to know that this can be used for astronomical purposes, somehow this man, Hans Lippershey, did not extend that. All that he had to do was use this at a different angle. So this is why we say it doesn't happen just by luck. It happens for a prepared mind. Somebody should be able to see the potential of this. Somebody should be able to see the real power of this. And only then accidental discoveries will be made to look very great discoveries later on. Okay, it doesn't happen to everybody. So it is like a logician. A logician is somebody who reasons out everything. Why does this happen this way? Why does it not happen that way? No? This is called logic. You try to give reason, assign reasons to everything that happens. So if you give a drop of ocean, if a logician knows that there is a drop of water that is possible, now you can in your imagination build an ocean. Do you see that? All you have to do is, what is it that you have to do in order to make an ocean out of a drop of water? Keep adding them mentally. So if you have the concept of a drop of water, it doesn't take much time for you to realize that an ocean is possible. So an ocean will not surprise you. After all, you say ocean is made up of drops of water. Okay, in the same way, Galileo's use of telescope for astronomical purposes proved just that. So Galileo came to know about the spyglass, but then Galileo must have had a hearty laugh because this man Hans Lippershey was on the doorstep of making a phenomenal astronomical contribution, but somehow he failed to turn his telescope towards the skies. Okay, so Galileo was the fortunate one, or we say Galileo had the scientific brain. Some phrase that I used very often. Accidental discoveries happen to whom? To a logician, yes. To what kind of a mind? A prepared mind. Okay, to a prepared mind. So Galileo's mind was a prepared mind. Therefore, he was able to put the telescope to wonderful applications, and rest is history, as they say. Okay. So what are the things he did? And I have a purpose for every slide that I am showing you here, because I know that I am addressing high school children or maybe even younger than that. High school. So I have some motive in putting every slide here for your age group. Now this is Galileo's telescope, and the telescope that you are making tomorrow, the assembling, is far, far, far better than this telescope in many ways. Now does that make you better than Galileo? Who knows? I don't want to take away anything from you. There could be somebody who can do something better than Galileo. But you should first know what Galileo did, what were the methods by which Galileo arrived at these things, and then if you followed those footsteps and maybe put a little more, you'll be able to do better. But for that you should be a prepared mind. Okay? So this is going to come again and again in today's session, prepared mind. So Galileo made this telescope which has just a 3-inch diameter. I don't remember numbers very clearly, so you should correct me if I am off. I think it was a 3-inch diameter. And what's the diameter of the telescope that you are going to assemble? 5 inches, huh? 5 inches. So it's 2 inches more than that. Now, what are the benefits you get by having a telescope which will be 2 inches more than that is something that we will see a little later. And the other thing is that Galileo's telescope made use of lenses. I think your telescope will be making use of mirrors. Okay? Of course, eyepiece will have lenses. Huh? It will be a reflector telescope. Now this, what you see on the left hand side, can you guess what this is?
Sir, Jupiter and its positioning of moons over the days which Galileo.
You have seen this before? Then how did you guess?
Sir, last session we had that Galileo saw.
Torsidra? Oh, okay, okay. Fine. That's fantastic. Then it reinforces what Mr. Ravi has already mentioned. So this is not Torsidra, not okay. Okay. Only the movements. So, you are able to connect that animation with this. That's fantastic. But Galileo did exactly the opposite. He had this static one and he created the animation in his mind. There is a big difference between the two, because these are the Galileo's notes on different dates. He puts the dates there, and then he shows Jupiter is here and 2 dots to the right, nothing to the left. On the 30th he sees 2 dots to the left and 1 to the right, then 3 dots. Look at the position of the dots and also the spacing between them. The spacing between them. If you were to actually make a telescopic observation of Galileo's, these are called Galilean satellites after him, which you can see through your telescope very easily. If he could see through 3-inch telescope, you can definitely see through a 5-inch telescope. You should be making this kind of diary. It's absolutely important. Don't go for fancy things like some Canon SLR camera or DSLR camera or some CCD device and other things. Okay, they can all wait. But the right way to start is not to use too much of technology. You go on using better and better technologies with passage of time. First, you should know how to do this manually. So if you are looking at the moon through the telescope, make a sketch of the moon as you see through the telescope. If you are looking at the Jupiter satellites, suppose you have some 20 nights which are very clear, 20 consecutive nights, then if you make a diary like this, you will exactly be walking in the footsteps of Galileo. And that itself is a very big achievement. You know, psychologically you feel that you are Galileo for a moment, because you are doing exactly what he did. And this is not something which is impossible for any of you. Okay, all of us can do this. So please do this. And what he inferred was that these dots are actually going around Jupiter. The animation that Mr. Ravi showed you, that animation is not easy, because all you are looking at the sky is the position of the dot today, tomorrow, day after. No. And then to put together, I may always say that there are new dots that are coming every night. Nothing can stop me from saying that. But then to come to the right conclusion that that is wrong, what I am saying is wrong and what Galileo has done is right, that itself is not very easy. So you should convince yourself by doing this exercise. Will you? Please try this. It's not very difficult. So the reason why I brought this up is the first observation of this Jupiter was made on 7th of January 1610. What's the date today? 10th of January. Okay. Is it 20 minutes over or 20 minutes remaining? Oh. It just said 20 minutes. So.
I was born on 7th Jan.
See, it's a Jupiter. Good. Okay, so you can do these kinds of things. So in the able hands of an investigator of nature like Galileo, telescope brought in a big revolution in astronomy, because by knowing that the planet Jupiter has some celestial object going around it, it at once told that in those days it was believed that Earth was the only object around which all other things went around, the geocentric theory. But then this one showed that, this did not show that geocentric theory is right or wrong, this simply showed that there is nothing special about Earth. It showed that if Earth has something going around, then there is something else also in the sky around which something going around. Okay? So nothing special about the Earth. So that was a big achievement for his time, though many people did not believe him in those times. Okay? So on the left hand side here you see the sketch made by Galileo about the moon that he observed. On the right hand side you have the actual photograph of moon. Okay? Now if you look at, if you compare these two, see how wonderful the observation of Galileo is. Okay? There are many other things that he did. Unfortunately we can't go into the details of all the things that he did. I leave it to you to read more of Galileo's telescopic observations. But the important thing is that even with that small telescope, which we call primitive by today's standards, it's very primitive compared to today's telescopes, the one that you are going to assemble tomorrow, but he could achieve so much. So even if you don't do something more than that, it will be a very, very good exercise for you to do everything that Galileo did to start with. Then you do other things. Okay? So these are all some of the great big telescopes that people later made. With technology you can always make this. See, the first important thing is that to know something can be there. Once you know something can be there, then you can go on making it better and better and better. Until the time you did not know that telescopes can be made, it has taken mankind 4,000, 5,000 years to make the first telescope. But the moment the first telescope was made, you know that something like this can be done. Then to make better and better telescopes, it has hardly taken 300, 400 years. So in 400 years, the evolution of telescope has been very, very rapid. But the first thing is to show that it is possible, that it can be done. And that's what Galileo's telescope did. Okay, so, and most of the telescopes were lens-based ones, early telescopes, and then came mirror-based telescopes, the one that you are going to make, a reflector telescope. Okay, they're also called Newtonian telescopes. But why this turnover? Why did you want to change from using a lens to a mirror? Yeah. Okay, so you've discussed that. Not much. Okay, fine. Yeah, what you're saying is absolutely right. So, you want to add something to that? Yeah.
Yes, sir. And plus, they were because the convex lens acted
As a prism. Okay. Huh?
and they were more difficult to handle with, and
The lenses were hard to make. I don't have to give this talk now anymore. It's all over. Okay, it saves my time also. Fantastic. What you're all saying is right. So making big lenses were difficult. Even small lenses are difficult. Then having some false colors because of the lenses That was another problem. So for those things, he came to this. But there's a small different take that I have, a different way in which I want to present the same thing. So for that purpose, I'll complete my slides. Okay. So this is how it was. Now immediately one thing that you'll notice is that the telescope length itself has become pretty short, small. Okay, compared to Galileo's telescope, which is much longer. Already you see that the Newton's telescope is smaller. So with reflector telescopes, that is possible. You can make more and more powerful telescopes, but not which are really very long, much smaller than lens-based telescopes. Okay, so the two problems were related to, one is called spherical aberration, the other is called chromatic aberration. Chromatic aberration is what you told, that there are some false colors. Spherical aberration is because of the geometry, because of the spherical nature of the, you make a convex lens or a concave lens by using a spherical object. Okay, I have a spherical object like a glass sphere like this. So out of this you have to scoop out, you have to remove the unwanted material, and you can make a convex lens out of this, of whatever focal length you want. Okay, so whatever the lens that you make, concave, convex, it will be part of the sphere. Therefore they are called spherical lenses. Okay, so these spherical lenses have, because of this geometry, what is called spherical aberration. Now what does that spherical aberration look like and what chromatic aberration looks like, I'll quickly go over in the next couple of slides. It's the same sphere through which I have taken the photograph of a mesh. Then you see that only at the center you have undistorted picture or image of the mesh, and as you go towards the edge you find these curvatures. Now that is not a good thing. So your image is going to be distorted. No matter what you do, spherical aberrations will always be there if you use a spherical lens or a spherical mirror. Okay, so this is what happens. You have parallel beam of light going through this lens, which is a spherical lens. The focus is not a point. Some rays which are at the edge of the lens come here, and some rays which are closer to the center of the lens go there. So there will be a spread. This is called the circle of confusion. Not confusion as we get confused. Okay, fusion, confusion. Fusion is putting together, confusion is spreading out. Okay, in that sense. So what it means is, if you have a point object here, if you have just a point, suppose you have a star, the image of the star here will not look like a point. The image of the star will look like a disk. It will be extended. It will be looking like a disk. That's the effect of the spherical aberration. So this is something that you cannot get over at all. Okay, and just because you are high school children here, I have ambitiously put a few things which are non-astronomical, just to drive home the point that nature has anticipated these problems, spherical aberrations, and it has beautifully solved them. And when you come to know about that, you can also use the same solution for your making of telescopes. Okay, so one solution is, don't use a spherical lens at all. Distort the shape of the lens slightly away from being a spherical one, or you use what is called a non-homogeneous lens. I'll explain to you what it means very quickly. So this is one solution by nature, where a microscopic organism called Pontella, okay, you can study more about that, if you just jot down somewhere, you can go back and look up on the internet, this Pontella. This is the eye of the Pontella. So if you thought that your eye is very superior with one lens, Pontella is better than that. It has a system of 3 lenses. So with the help of these 3 lenses, you can immediately see also that the geometry is not spherical, it is slightly of a different geometry. Because of that, all the rays from the edge to the center, they are brought to a focus at one point. So if you are looking at a star through a system of lenses like this, a star which is a point will look like a point to you also. So it's better to have a Pontella's eye rather than the ones that we have. Or if you want to make a telescope, don't make a telescope with one lens, you make a telescope with a system of lenses which will overcome this problem. So this is nature's solution. Through the course of evolution, this is what has happened. Then fishes are known to have a spherical lens, real spherical lens, a single lens which is spherical. Physicists were actually surprised that the eye of the fish did not have a circle of confusion like this, but the focus was perfect. Now how can that be? If your physics is right, all spherical lenses must show spherical aberration. Now here is a fish eye which has a spherical lens, but there is no spherical aberration. So either physics is wrong or fish is a magician, right? One of the two. Magic has no place in science anyway. So we have to figure out what is the magic behind this, what is the science behind this magic. So what we found out was that in this spherical one, as you go from one end to the other end like this, refractive index is not the same. You know refractive index? Do you know what refractive index is? You know refraction of light? Yes? So for example, if you take a point of light, it is there. Now I bring a lens. I had two lenses here. I don't know where I put my lens. Anyway, so you have the spot there. Now I bring the lens in the path of light. Now see that you'll see that the spot has shifted. It may be blurred, but it has shifted. It is there and it is here. So there is so much of a shift. So the bending of light is what we call refraction. It happens when it passes through materials of different density I will use for the time being. It's not a really perfect way to say, but it's acceptable for the time being. Okay, different refractive index. That makes sense. Okay, so you have this. Now it is like having one lens in which refractive index is continuously changing along. Now how can you make, if you take this one, any part of this lens will have the same refractive index. Now it is like having a single material in which refractive index is constantly changing from the edge to the center. Now because of that, what happens is, and again it is changing in such a way that all the rays which are bent, they come to a common point of focus. That is asking for too much. This is an engineer's delight. You know, if you are an engineer, to make a lens of this kind, you would be extremely happy to achieve this. But fishes have done that very effortlessly. Okay? Now the solution to this is the following. The solution was given by this gentleman, James Clerk Maxwell, whose contribution to electromagnetism is great. What he had theoretically shown, he did not have any object which behaved like this. He calculated, he showed that if you have an object in which from one end to the center the refractive index is changing, you know, each circle here is of a different refractive index, then light will bend differently at every point and it will come to a focus. So fishes have done that. So if you want to make a telescope without a spherical aberration using lenses, then the only way to do is this. Okay? Get fish eye. Big enough. Okay? So that's one, and I think how many minutes more? Over.
That's okay, sir. We can extend 10 more minutes.
How many more minutes?
10.
10 minutes? Then I have to show some experiments.
That's
quickly. So in which case, I'll rush through a few of the slides because you already mentioned. So telescopes have this chromatic aberration. This is the false coloring that you get at the edge of the lenses. Therefore, you don't need this. Now, if you want to understand why there is spherical aberration, why there is chromatic aberration, you need to understand light. behavior of light. Therefore, Newton knew this problem. You know Isaac Newton? Isaac Newton knew this problem, that lenses have this kind of a false coloration in the image. To understand that, he did not tinker with the lens. He said, I should go to the root. The root of the problem is understanding what light does when it interacts with matter. When it falls on anything, what happens to light? Those changes. Okay, so this was the classic experiment that he did, and he showed that chromatic aberration actually comes because of this refraction of light through a prism. And you see the separation of colors here. So the separation of colors happen because for different colors, the angle by which light bends will be slightly different as it passes through prism. So if you have white light there, then what you get is colored light here. All the colors which make up this particular white light, then all these colors are bending at different angles, so there is a separation. Okay, and nature also does it, but here we don't complain that we have a problem, chromatic aberration. So if you, this is actually the photograph of a sunset, and when the sun is very close to the horizon and under certain conditions of the atmosphere, you can actually see that the disk of the sun breaks down into different colors and they get separated out. So this is a prism experiment that we saw before on a grand scale. On a very big scale, you have a prism as big as the Earth's atmosphere between you here and the sun there, the sun's atmosphere, the Earth's atmosphere. As sunlight passes through, it splits into different colors. So you can actually see this. This is called green flash, by the way. So people actually spend enormous amount of time, and they should have patience to see one green flash in their lifetime. Okay, but this happens. This is also chromatic aberration. So Newton did all that, but if you use a mirror instead of this is a concave mirror. Okay, you have a concave mirror of this kind. So if you have a concave mirror and you send different colored lights, they all bend and come to a focus at the same point. So no chromatic aberration. This is what Newton discovered. So no lens. A mirror was a better one to solve that particular problem. Now the next thing that we need to know about telescopes is what is known as resolving power. This is perhaps the most important feature of a telescope according to me, because this will actually decide what are the objects that you can see in the sky and with what kind of clarity. Okay? So by resolution, what we mean is the following. Here you see two objects which are separated. Okay, we say this is well resolved. Okay, this is well resolved. Here there is a bit of a overlapping between these two. Some amount of light from this, some amount of light from that are occupying this particular space, because of which it doesn't look like two different objects. It looks like a single object which is like a dumbbell. Here you don't see the two objects which have been embedded at all. So this is very poorly resolved. The two are merging into one. Here they are just about separating out, and here they are completely separated out. So when you make a telescope, you always make a telescope to improve the resolution. Okay? And it is not for magnification. For astronomical purposes. For astronomical purposes, the telescopes are designed to make two close by objects to be resolved, two close by stars, for example, to be resolved, rather than make the small star look this big, which will never happen anyway. Because the small star will still be small star, but you can see more details because of the resolution. Okay? So this resolution is mainly because of, again, property of light. There is a certain limit to which you can resolve. Beyond that you cannot resolve. If two objects are closer than some distance, as seen from the earth, in the sky, you cannot resolve them. The reason is the property of light again. So this light has a tendency to actually spread out when it passes through a small opening. Okay? So for example, I have a slide here which has a small opening, everywhere else it is black. So this is how the spot looks. Now if I put this through that opening, do you see that the light spreads out at the center? So this is called diffraction of light. When light passes through very narrow openings, it will spread out. Diffraction or diffraction, depending on how you want to pronounce it. So that is diffraction. Now if you have more number of slits, that was one slit only. There was just one opening. If you have a number of openings of the same size, but a large number, then you will see that. Now how many dots can you see now? More clearly. Okay, so you can even count the number of dots there. The number of dots will go on increasing as you increase the number of slits and make the slit very, very narrow. And if you have one like this is how you see. See how well separated they are. Okay, this is a diffraction grating that I have.
Sir, can I turn off the lights?
Paravailla. That will take away 30 seconds of my time. Okay, so this is called resolution. You have very good separation. Now for this separation to be good, you can actually use this diffraction grating like that. Okay, that's just a reflection, don't worry about that. Okay, so that is the one. Now this diffraction sets the limit for your telescope. So how well that telescope is going to resolve will depend on that. Now what will this resolution depend upon? It is not only the fact that there is diffraction when the opening is very small. When the opening is much bigger, what you call an aperture, even then the resolution can be improved, as we will see quickly in the next couple of slides. Just to give you a flavor of what resolution means, this is Jupiter, same size. What's the difference? One is blurry, the other is not only sharp, there are lots of features that you can actually see on the surface of Jupiter which you don't see here. This is what resolution does. So when you make a telescope, it is not to make a big telescope in which this Jupiter will look this big, but it will be looking the same size, but it will have all the features very clearly visible to you. Okay? Of course, you can take a picture and then you can blow it up. If the resolution is good, you can blow it up to big sizes and you can see more details which you can't see on the screen right now. So this is what astronomers do. Okay? So telescopes are designed to possess very high resolving power rather than high magnification. So we don't want magnification. In fact, magnification is actually bad in one way, because there is a certain amount of light coming from a star or from a comet or from any light source, and now if that is going to be blown up into a bigger size, same amount of light you are spreading over a larger area. So what is the effect of that? It gets blurred. So magnification doesn't help. So it's better to have high resolution and small magnification, and the resolution is very good. Then you can take a photograph of the image and you can actually have large prints made in which you can see more details that you can't see in a small image. Okay? So this is another photograph to show. This is the first ever photograph taken of Andromeda galaxy. Look at the resolution, and this is something that you do in recent times, even with maybe some of the mobile phones can give this kind of resolution. This is what resolution does. Okay, so you make telescopes for that reason. And the other thing is, for this resolution, the size, the aperture is very important. I told you about Galileo's telescope, which is just 3 inch in diameter. What you are making is 5 inch in diameter, which is much bigger. Okay, and it also depends on one more factor called focal length. So you'll be, I think somebody is going to talk about those things shortly next. What this large aperture or the diameter of the lens or the mirror does is that it is able to capture more light, just like this bucket can capture more rainwater than this one if both are kept one next to the other under same conditions. So this will have more volume of water than this in the same time. Okay, so this is another picture to show you that if the aperture is very large and the brightness is big, brightness is more, it's not appealing to us here, but the important thing is that the brightness will be more if the aperture is more. If the aperture is becoming lesser and lesser, then the image will be less and less bright. Okay, that's the point we have to appreciate there. And of course, again in nature we find this. All nocturnal animals have eyes aperture which are very, very large, and that's because they want to capture every single photon, every small amount of light that is available in the darkness. To you and me it may be pitch dark, but then for an owl or for a tarsier that may not be the case, because whatever little light that is there, it is still able to imagine. Okay. Similarly, these net casting spiders, they have very good resolution. And this is the last bit that I would like to discuss for 2 minutes exactly. Is it okay? So now somebody will be talking to you about this F ratio and F number. No workshop on telescope will be complete without a discussion on F number and F ratio. So what it just means is that the ratio of the focal length of your lens or the mirror divided by the aperture diameter, the opening of the telescope which is collecting light. So what's the effect of that? If you take photographs of the same burning candle with the same exposure time, you are clicking for 1/90th of a second, you are keeping the aperture open, then this f1.8, what this f1.8 means is the ratio of focal length to aperture diameter is 1.8. What is the aperture of your what's the aperture of your, you are making f8, is it? You are making f8. So you are making f8. So you know the focal length of the mirror and you know the aperture of the mirror. If you divide one by the other, you should get 8. Okay. So if you change this f ratio with in a camera, when you take photographs, this is what happens. So if the f number is more and more and more, okay, what is the effect on the image? It is less bright. The brightness is becoming less. Of course, this may look more pleasing to the eye, but the point is that it is less bright. That's all we are telling right now. Okay, and the f ratio of a human eye is about it changes from 2.1, 2.2 to about 17 or 18, because we have the ability to change the pupil size according to the brightness. It happens involuntarily. You don't do it. You go out into the sunlight now, suddenly you will have the tendency to shrink the pupil diameter. Okay? So the pupil diameter ranges from about 3 millimeter to about 6 millimeter or so, 6 or 8 maximum, and the focal length is about centimeter r centimeter, about 6 centimeter. So if you now divide a focal length by the aperture, you will get the f ratio. But it's not constant for us because it keeps changing with outside brightness. Okay, yeah. So these are all some of the things, and okay, that's a good point to stop. So in conclusion, what we would like to convey is that building a telescope is not putting a few elements of the telescope together, fixing with nuts and bolts, and then getting a device ready. The whole design is based on properties of light. What happens to light when it falls on a mirror, when it falls on a lens, and when it interacts with other things. And secondly, the design of a telescope is always in the direction of making high resolution rather than high magnification. Okay, so that was the part. Now the things.
Sir, 5 minutes. Okay, sir. Done.
ತಂದ್ಬಿಟ್ಟಿದ್ದೀನಿ ತೋರಿಸ್ಲೇಬೇಕು.
Sure.
I'm sorry.
No problem.
Whose is the next session? Then I'll apologize to all of you that because of me there is a delay. Now the thing is, I'll circulate these objects to you. You can just take around in 5 minutes time and look at them. I'll tell you what you have to do. This is a diffraction grating. You can look at any source of light there through this grating. You can see the kind of spectrum that you get, the spectrum of that light. Similarly, you also get a spectrum using this prism. You need to compare which of the two spectra is more bright, more resolved. Now you understand what we mean by more resolved. What do you mean by that? If the resolution is more, better details you see, so more colors you see. Okay, so this I will circulate this way, and idana a corner in the madbidana, so that there is a good distribution to the whole population. And then to know what diffraction or diffraction does, I have lycopodium powder in this. Each powder particle is spherical. What the effect that you see is the net result of all the particles, but it would be more or less the same if you were to use just a single particle. Like I did a single slit and many slits, one opening and many openings, it's the same thing. What you need to do is, do you have mobile phones with you?
No.
That's very good. Unfortunately, it should not have been in this session. We should have had a mobile phone. Then what we will do is, one of you can actually go around with a this torch, and then can you see through this? This is the problem with light. You have to be in the line of sight. Okay, so if you are to actually, this is beautiful. Okay, one of you can hold this. You can come one by one, the other one at this distance. You can stand at this distance, one of you. Please come. Here. Okay, there. So one by one you can come and look through this. You can have okay. The other thing that I wanted to show you is, the spherical aberration using this. Okay, spherical aberration. So if you look at, if you have some sheets in which you have, I should have brought that grid. Grid tara jana ididre. In your notebook you have those lines, parallel lines.
Yes, sir.
Okay, so place this over the parallel lines and see how the lines will be distorted at the edges and how they are not distorted at the center. Okay, so please pass this on.
Quickly, one after the other, quickly go to see that. Quickly, people have not seen.
Now we can switch off these lights. So I would like you to observe this those of you who are not engaged with something, observe this path of light in this. Okay, it's bending. It's bending gradually.
It looks like some lace.
It's bending gradually. It should have gone straight parallel to the surface, but it is gradually bending there. This is because I have taken some amount of water, carefully added a little bit of concentrated sugar solution. That sugar solution mixes with water unevenly, so you have small change in refractive index as you go from top to the bottom. This is what happens in the fish eye, because of which the spherical aberration is not there. Okay. Yeah, if you go down where there's only water, it is straight line. But you come up, then it is bending. Okay? If anybody wants to try, they can do that. Yeah. So I am done. Thank you.
Questions to sir?
Okay, guys, if you guys have any questions to sir, you can post it.
Anyone? Questions right now?
Yeah.
What is it?
I got a sphere. I wanted to ask about it.
Here, it's here. Here is here.
So you, even these lines and these lines are both are same. You need not draw this. You can actually do it.
I'll mesh it, alva.
Sir, how does the light bend in the sugar water, but then it goes straight in the normal water?
In the normal water, throughout, the density of water is the same. Now, at the top where I have poured some sugar solution, sugar has not completely mixed with water throughout. It will take some time. So there is more sugar which has dissolved at the bottom, and there is less sugar that has dissolved at the top. So there is a gradual change in the density. So light also bends gradually because of that.
From the grating.
It was more clear in the grating?
Sir, from the sphere, the glass sphere, I saw that normally you are able to see that inverted thing also. But if you point it at the board and then do like this, you are able to see rainbow kind of a shape. So not shape like rainbow kind of color. So why is that? If you are pointing,
It will also have chromatic aberration.
Oh, it's due to that.
It's due to that. Good question. Sorry, Bharat.
Hey, no problem, sir. No problem. She has a question.
Yeah.
You have a question? Yeah.
Actually, when we look in the sphere, there's both a concave and convex lens side. So when we look through both of them, I couldn't place after seeing the sphere what was the image.
You could not?
I couldn't place what kind of was it direct image or anything. So in the end, what kind of image?
It will get distorted. At the edges, it will be distorted.
So it cannot be erect.
That cannot be changed at all. You cannot correct it at all. You have to either change the shape or you have to change the refractive index. One of the two. So fishes have done by changing the refractive index. Fontella has done by changing the shape and also having more than one lens. So these are the 2-3 solutions that are possible for spherical aberration. No other solution, only these. Nature has invented all of them.